Today we're going to be talking about exponential growth and exponential decay and what those equations look like, what the graph looks like, and what the table looks like for each one of those. So we're going to study this in the context of the great classic Alice in Wonderland. So there was a scene in Alice in Wonderland where she needed to fit through a door and she needed to shrink. And if you read here, she needs to be 3 inches tall, and her height decreases by half each time she takes a drink. So we're going to make a table here, or we have the table here, we're going to fill it in. And on the X, the first column is going to be the number of drinks from the bottle. And we're not going to worry about the feet because we're trying to figure out when is she 3 inches tall. She's starting out at 48 inches tall. So when there are 0 sips gone from the bottle, when she hasn't taken a sip yet, her height is 48 inches. Now she takes 1 sip and her height is going to decrease by a half. Again, we have that underlined up here, 1/2. So if you do 48 times 1/2, you are going to get 24. Then another sip. So when she takes another sip, she's not going to lose 24 inches of her height. She's going to lose half of 24. Well, 24 times 1/2 is 12. And then another sip, it'll be half of 12, which is 6. And then the next sip, half of 6 is 3, which is the height that we needed for her to get through the door. So you'll notice in the table that the height is not going down by the same amount each time. We went down by 24 inches, then we went down by 12 inches, then we went down by 6 inches, then we went down by 3 inches. So what I want to write here is like when we go to the next value here, we times by 1/2. Next one, we multiply by 1/2. Next one, times 1/2. You're multiplying the previous value by 1/2. When we had a linear function, we would add or subtract the same number each time. We're going to add 5 each time or subtract 3 each time. Here we are multiplying by 1/2. Let's make a graph based off of this, where the x coordinate, or the x-axis would be number of sips from the bottle, and the y-axis will be the height. So 1, 2, 3, 4. Those are the number of sips. And for the y-axis, I'm going to go up by 3s so that we can make sure they all fit. The issue that you're going to run into with exponential functions, especially when you're graphing them, is fitting them all on the graph, because they're going to get large really quick, or they're going to get small really quick, as you can see from this one. Okay, we're starting at 48. And then we're going down to 24. And then we go down to 12, then 6, then 3. So this graph looks like this. You see, it's going to get closer and closer to 0. And we're going to write an equation based off of this. So to write an exponential equation, y equals, our starting value is going to come first. Where did we start? Well, we started at 48 inches. So we do 48 times our growth rate, or in this case, our growth rate is actually 1/2. It's a fraction. Times 1/2 to the x power. So that is the equation for this. For any exponential equation, we talked about this the other day. Remember, a times b to the x, where a was your starting value and b was your growth rate. Then what was the y-intercept in inches? Well, if you look at the graph, the y-intercept is 48. The y-intercept is 0, 48. It's a starting value. It's where we touch the x-axis. Sorry, not the x-axis, the y-axis. Touch the y-axis. And it has no x with it. So if you look at our equation, 48 is just hanging out by itself as being multiplied. There's no x with it. The 1/2 is where you see the x. It's 1/2 raised to the x value, or to the x power. In your equation, what is the b value? Well, the b value is your growth rate. It is 1/2, and this is the growth rate. This is the growth rate. It is the number being raised to the x power. So whenever you're given an equation, an exponential equation, you look and see what number is being raised to the x power, and that is going to be your growth rate. Now, what line does your graph appear to be approaching but never crossing? Well, if you think about it, every time Alice drinks a sip from the bottle, her height goes down by 1/2. So, we stopped at 4, but if she took a 5th sip, okay, half of 3 is 1.5. She takes another sip. Half of 1.5 is 0.75. So she keeps taking sips, and she's going to keep getting smaller and smaller, but she's never going to be 0 inches tall. She's going to get really, really close, but she will never be 0 inches. So what line does your graph appear to be approaching but never crossing? It is the x-axis, because on the x-axis, your y values are 0, and her height will never be 0. So even if I plug in a number like 200, you're going to get a very, very small number, but it will not be 0. You can't multiply a number by 1/2 and get 0, unless that original number was 0. So the x-axis. We call that an asymptote. This is called an asymptote, and we're going to use that word later on when we start graphing exponential functions. But an asymptote is a line that your function gets closer and closer to but never touches. So our graph is getting closer and closer to y equals 0, or the x-axis, but it will never touch that. So x-axis or y equals 0. Does this situation represent exponential growth or decay? This represents decay. And by looking at the table, you would say all the y values are going down. Or by looking at the equation, your b value is less than 1. So that is how you can tell if your situation is exponential growth or decay. And if you're just given a graph, your graph is going to start large and get smaller and smaller as the x values get larger. All right, in number 2, now Alice is going to grow back to her normal size after eating cake, a bite of cake. Her height doubles, but she's eaten too much and she's growing to not 16 feet tall. We're going to keep with inches, 192 inches. So we're going to make a table again based off the previous situation. So we're going to ignore the height. So number of bites of cake. Now her starting height is not 48 anymore. At the end of this situation, she was 3 inches tall. So before she takes her first bite of cake, she's 3 inches tall. And every time she takes a bite of cake, her height doubles. So 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48. 48 times 2 is 96. And 96 times 2 is 192. So again, if you're looking at the values over here, we'll call them the y values, we're multiplying by 2 each time. All right, we're multiplying the previous value by 2. And we're going to graph this as well. So on the x-axis, we'll do the number of bites of cake. And then in the y-coordinates, we're going to go up by tens. Going up by 3s like we did last time, we would not have enough room on this graph. And you're going to find that for the first couple points, it's going to be hard to plot those points. And that's okay. You're just going to need to get close enough so that I can understand what those points are. So 0, 3, okay, that's going to be really close to the x-axis. Then we have 1, 6, so it gets a little bit larger. 2, 12, okay, so it's above 10 now. 3, 24, okay, so between 20 and 30. 4, 48, so pretty close to 50. 5, 96, so really close to 100. And then 6, 192. So you see how fast this grew. So that's what your graph would look like. So an equation for this would be y equals, our starting value was 3, and our growth rate was 2. Because we multiplied the previous values by 2 if you're looking at our table. Does this graph approach but never reach a certain value? No. Like, look at, if we kept going, if we multiply, if we took another bite of cake, 192 times 2 would give us an even larger number. So no, the graph keeps going. Does the situation represent exponential growth or decay? This is growth. And you know this because the y values are going up. And b is larger than 1. Okay. And then summarize exponential growth and decay. We're going to use this table here to summarize it. The equation for both of them is the same. Y equals a times b to the x power. So the equations look exactly the same. A is the starting value in both. Starting value. A is a starting value. B is the growth rate in both of them. Growth rate. But in exponential growth, the growth rate is greater than 1. In exponential decay, B is still the growth rate, but it is less than 1. And then what the graph looks like in exponential growth, that was just like the one we had. The graph goes up really quickly. And in exponential decay, the graph goes down really quickly. So that's what the two graphs look like. So we're going to spend some more time comparing what does exponential growth and decay look like, and where are some real life examples that we see. So thank you for watching this video. Make sure to smash that like button and subscribe.